Alright, so in this video, we will go over the normal distribution and the central limit theorem. So the normal distribution is also known as the Gaussian distribution. It is a type of distribution for continuous variables. And it's a distribution where the expectation of x or the mu of x is located at the center of the distribution. So right over here. And then the curve is symmetrical around the mean. The axis, or like the variability around the mean, is given by the singular values of the standard deviation. So one negative standard deviation to one positive standard deviation, that will make up around 68% of the normal distribution right here. So if we right over here, that makes up around 68% of the distribution. And then from the -2 standard deviation to 2 standard deviation, that will make up the majority of the distribution. So just from going right here, these parts are left out. That makes up around 95%. Which we can interpret that as 95% of the random variables within the normal distribution are located within 2 standard deviations of the mean. So the probability density function of the normal distribution is given by this formula right here. Given that the range is from -infinity to infinity, because theoretically any random variable can be place at a very large, or very low value, or very large or very negative value. But this formula right here, it's not, we're never going to actually plug in numbers to like find what the normal distribution actually is, or how we can find a function. But what's important is that we know that the standard normal distribution is when the mu is equal to 0 and then the variance equal to 1. And we'll denote that as the normal distribution of mu and then the sigma squared of variance right here. So for a standard normal distribution, the mu will be 0, and then each standard deviation will be one value each, if we go left and -1. So it's made much more simple. And so if we're not mathematically plugging in the values for the PDF function, why are we using why are we learning about the normal distribution? And that's where the central limit theorem comes in, short for CLT. So the CLT states that the distribution of independent variables becomes closer to a normal distribution as the sample size n increases. So I'll draw three distributions with varying sample size. This is just a hypothetical, but let's say we have a sample size of 10, so fairly low. Then we might get like a distribution of something like this. That's not a very good graph. Okay, so this obviously is not a normal distribution, because it visually looks like the distribution is skewed to the right, and it's not symmetrical around the mean. So if we use a slightly larger sample size, we might get something like this. Maybe a little closer to the normal distribution, but still not the most symmetrical. And then if we use a larger sample size, I use 30 because typically 30 is the kind of the cutoff of whether we can actually use a normal distribution for the central limit theorem. Usually, if the sample size is less than 30, we can't. We usually say that we can't apply the central limit theorem to our probability functions. But anyhow, if the sample size is sufficient enough, in this case, if it's 30, we'll get a distribution that's that is fairly similar or close to the normal distribution. All right. So the CLT is helpful when we're doing parametric testing and creating confidence intervals. So I'll go over that in future videos, but it is, the whole point of it is that it's a very important theorem. It's kind of definitely one of the most important theorems in statistics, not calculus. But it's also important for finding out the z-score. So let's say that for a standard normal distribution, we want to find a probability of a random variable landing within 1.24 standard deviations or less. So visually, if we draw a normal distribution, let's try that again. Okay, well, good enough. If we draw a normal distribution and then we'll draw one standard deviation of it and then two right here, we want to find the probability of a random variable, and we're assuming this is standard, right? Okay, so we're assuming this is a standard normal distribution, so we want to find a probability of a random variable landing within 1.24, so this place is around 1.24 or less. So all of here, excluding any standard deviation that's greater than 1.24. And so we would simply say that the probability of, this is the Greek alphabet Z, I usually just call it Z, but I learned it, all my teachers in the past call it Z, so I'll call it Z for now. Of Z being equal to or less than 1.24, say is I believe it's called phi, I'm not sure, but the phi of 1.24, and for standard normal distribution we can just look up that in the table. I'm not gonna go through it right now because it is fairly simple. We just have to make sure that we use a cumulative normal distribution function, not the one with the exact probability. But if you look that up, it should come out to 0.8425. So that is, we have an 84.25 chance of a random variable landing within 1.24 standard deviations or less, which makes sense because this part of the area looks like it covers up most of the normal distribution. All right, let's try a little harder example. So let's say we want to find the probability of a random variable landing within negative 2.14 through 0.77. So we will write that as the probability of z being equal or less than 0.77 minus the probability of being minus the probability of z being less than minus 2.14. And then, so when we're using a cumulative density function, we can't, the negative values for the z-scores aren't available. So we kind of have to rewrite this in a way where we can utilize positive values instead. So probability of z being less or equal or less than negative 2.14 can be written out as 1 minus the probability of z being equal or less than 2.14. All right. So once again, if you look up that in the table, this value should come up to 0.7794. If you find the probability of z being equal or less than 2.14 and then subtract 1, that from 1, it should come out to 0.0162, so a very small number, which equals 0.7632. So we have a 76.32% chance of random variable landing within these two intervals. Again, this intuitively it would make sense because there's not a big chance that the random variable, if it lands in a negative value, it won't very small chance that it'll land below 2.14. And then 0.77 is relatively close to 1. All right. For the third example, say instead of being given the z-scores or the standard deviations, see, we're actually giving the numbers in relation to the normal distribution, and we're assigned to find the probability of a random variable being within the two given numbers. And so if you want to do that, we can write out this formula right here, below here. The probability of x being between from a minus mu divided by the standard deviation, and then the upper being the b minus mu divided by the standard deviation. And so notice the reason why we do that is because if we're using a standard normal distribution, then the mu here is 0. And then the standard deviation is 1. And so that just comes out to be this function right here. And so when we're trying to find the probability of these two numbers, given that it's not a normal distribution, we're subtracting the mu and then dividing by the standard deviation because we're standardizing or normalizing it. Well, we're not normalizing it because it's already a normal distribution, but we're standardizing it so that the mu can become 0 and then the SD can become 1. But in this case, if we're assuming that we're using a standard normal distribution, we would simply just say probability of x being less than 1 minus the probability of x being greater than -1. Actually, I think I made a mistake over here. So probability of z being less than or 0. This is correct. This is not correct. So let me erase this. So this should be greater than -2.4 because z has to be greater than -2.14. And then when we subtract by 1, we will switch the sign. All right. So yeah, we set up the notation, but again, we can't utilize negative values in the table. So we'll write this out as 1 minus the probability of x being equal or less than 1. And then from that we get 0.8413 from x being equal or less than 1 to minus 0.1587. Again, we have to subtract by 1, so make sure you don't make that mistake. That comes out to be 0.6826. And that should be a number that we're familiar with because that's like I mentioned above, that's the probability of a random variable landing within one standard deviation. and that's what we measured here from -1 to 1, because we are using a normal standard normal distribution. All right, so if we're not using a standard normal distribution, we're using the normal distribution where the mu is 3 and the variance is 16, then let's try to find the probability of an RV landing from 4 to 8. So using the formula up above here, we'll rewrite that. So probability of 4 minus 3 over square root of 16, being the lower value, and then the upper limit being from 8, and then we're standardizing it by subtracting 3 and then square rooting by 16. This comes out to be 1 over 4. So we'll write that out as the phi of 5 over 4 minus the phi. So this one's given right here. This one's given right here. This is an unknown variable, so we're not including this in part of our final equation. Phi of 5 over 4 minus phi of 1 over 4. And since we normalized it, we can actually use these 5 over 4 and 1 over 4 within in the z table. So using that, we get a final value of 0.2957. So around a 30% chance that a random variable falls within 4 to 8, given that the mean is 3 and then the variance is 16. So relatively low chance. All right, that'll do it for this video. In the next video, we'll go over the chi-squared distribution as well as the t distribution and the f distribution. I won't include the specific tests for those, but kind of the general concepts and why they are important.